In this video, we're going to take a look at section 2.2, which is on functions. A function is any relation in which, for each element in the domain, which is typically referred to by the variable x, there is only one corresponding element in the range, which is typically referred to as the variable y. So this definition is really important for the material in this section. Typically, at least for my class, I don't usually have a question on the test that asks you to recite this definition, but if you don't understand the concept of the definition, you won't understand how to get the right answer on the problems that are related to the concept of function. All right, so what's really going on here is that whenever you pick a value for x, there can only be one possible answer for y. That's what it means to be a function. You pick an x, and there's only one possible corresponding value for y, only one possible answer that you could get for y in that case. All right, and then if that's true for every possible choice that you could make for x, then the thing you're working with is a function. If you can find just one example of choosing a value for x where you would get more than one answer for y, then it ruins the whole thing and it's not a function. So it's very much in the spirit of one bad apple spoils the bunch, right? You just have to find one number that produces more than one possible answer for y, and it ruins the whole thing. All right, so let's apply this definition to a few different concepts here. So let's look at these, which I call maps, right? So these are maps taking values in the domain and mapping them with arrows to values in the range. So if we take a look at this first relation, we want to know if this is a function, if it has that property that for any value in the domain, there's only one possible answer in the range. And if you look at how the arrows are pointing here, when I choose 12 in the domain, so that's like picking x equals 12, what is it possible for y to equal? The only possible answer for y, if we follow this arrow, is that y would have to equal 1. So for this particular value of x, there's only one possible answer for y, which is the number 1. And that holds true for the other two values as well. So if I choose 19 for x, the only possible answer I could get for y is 17, according to the map. If I pick 20 for x, the only possible answer I could get for y is 1. Now, I happen to get the same answer that I got earlier, but it's still holding true to the concept of a function, that if I pick any number over here, there's only one possible answer that it corresponds with over here. Right? And so this will be a function. For each value of x, there is only one possible answer for y. So we would answer yes here, this is a function. Now contrast that with this relation over here. In this case, we don't actually have numbers, we have cities. But if I choose a city in the domain, which is like picking a value for x, so let's pick this city here, which is Detroit, how many different possible answers are there for y, for the range? There are 3 different possible answers for y. There's the Lions, the Tigers, and the Pistons. And so choosing this value of x, there are more than one possible answers for y, and so the answer is no. And I don't have to look any further into this. It might behave like a function everywhere else, but like we said earlier, one bad apple spoils the bunch. If you can find just one particular value of x that has more than one answer for y, look at all these answers we have over here, it's not a function. The whole thing is ruined. It's not a function. Right? So the difficulty with things like this that are not functions is the following. If I ask you, hey, what's that sports team in Detroit? You're not going to have a particular answer for me because there's multiple possible answers. Well, it could be the Lions if we're talking about football, could be the Tigers if we're talking about baseball, could be the Pistons if we're talking about basketball, right? So there's not a clear answer. Whereas if you go back to this, which is a function, if I say, hey, when x is equal to 12, what do we get for y? There's one concrete answer, which is y has to equal 1. If I say, what do we get when x is 19? There's only one possible answer, which is 17. So these you get definite, concrete conclusions, whereas when it's not a function, there's multiple possible answers to any particular question you might ask like that. All right, so the moral of that is it's easier to work with things that are functions than it is with things that are not functions. And so as we move forward in the course, we will try to avoid things like this and focus on things that are functions because they're just better behaved, they're easier to work with. Right? If you have an equation that you know is a function, we have some special notation that you can use in that equation. So this is read as f of x. That's how you read that. This is called function notation, and it has the following properties, which make it pretty valuable, or very useful, I should say. Can only be used in an equation that is a function, so you wouldn't use this notation in an equation that is not a function. It takes the place of the y variable, right? So if you have an equation like y equals 2x plus 3, after you confirm that this is indeed a function, which it is, I can confirm that for you, you can replace the y variable with this new notation. And so we would read this as f of x equals 2x plus 3. Right. This is not f times x. I know in any other context in algebra, this would be interpreted as multiplication because, when you have two things side by side like that, that's what we've been trained to think of, is that's multiplication. But this x, this part of the notation, isn't really there mathematically. It's only there for informational purposes. So really, all we have here is f. Inside of the parentheses, we have information about the variable that we're going to find on the other side of the equal sign. So this is letting me know the only variable that you're going to encounter in this equation is the variable x. And so we see that over here. What you can do with that notation is replace the x with a number. So for example, you could have something that looks like this, f of 2. Right? And what that tells me to do is, in place of the variable that's in this equation, we're going to plug in the number 2. So it gives me some directions on what to do. We're going to plug in a number, right? And so what I'll have is 2 times, in place of the x, I'm plugging in the number 2. So it's letting me know what to plug in. And I would get, in this case, 4 plus 3, which is 7. Right? And so we'd have this conclusion here that f of 2 is equal to 7. And what's great about this is it has a lot of information. It's very efficient information, right? So it's very condensed. It has a lot of information in a little bit of space, which is what mathematicians like. We like being able to condense a lot of concepts and thoughts down to as simple or as few symbols as we possibly can, because that's a more efficient way of, encoding that information. And so what this tells me is which equation was used, because here's the other thing about function notation that's not mentioned here. We can use different letters besides f. So we could also have another function, g of x, which equals 4x plus 1, let's say. Right? We'll just make something up there. When I look at this conclusion, I'll know which equation was used, right? That we used this equation to get this result. Not g, we used f. And for x, we plugged in the number 2, so x was equal to 2. And for y, we got y was equal to 7. Right? So that's a lot of good information contained in the symbols that we're using there. So that's why we like to use function notation. So the last part down here is in reference to what we just talked about. F of a equals the value of the y variable, right? So f of 2 is equal to, this is again, it's still the y value, it's still the y variable. It's the value of y that you get when you plug a in for x into the equation, right? Which is what we just went through right there. And we're probably going to have another example on that in just a second. But this notation is very handy. Now, in this course, this notation is introduced pretty early on, right? We're only in chapter 2. And then it doesn't really get used much after this. So it's kind of a shame. And it's not the textbook's fault. It's just the content that we're going to be covering in intermediate algebra as we go forward doesn't have very many opportunities for using function notation. So they will use it when the opportunity presents itself, but it's just not going to present itself very often. In college algebra, however, this notation is very highly used. And so you will see a lot of this function notation in college algebra. Once it gets introduced in that course, it gets used very heavily. So, all right. So let's take a look at an example here. So we have the given the function k described by this. That's kind of a weird letter to use there, but we'll go with it. K of x equals 4 times x. Find each of the following. Right? I don't know why I put parentheses around that. Let's write it the way we see it in the directions. So 4x. We want to find the following. So I don't know if I'm going to do all 3 of these because it'll kind of get repetitive. I'll just do the first 2. and leave the last one for you. Now, it's kind of a big number, but I think you'll get the hang of it after we do the first two. So for part A, we're being asked to find k of negative 11. So again, without having to use any words here, I know exactly what to do with this. I know which equation to use. We're going to use equation k. And I know that having a number here tells me to plug negative 11 in for the variable. All right? So everywhere I see an x, I'm going to replace it with negative 11, just like they did in the function notation. So on the right-hand side of this equation, in place of the x, I'm going to plug in negative 11. And I'll multiply those together. 4 times negative 11 is negative 44. And so I get this conclusion. Now, sometimes I'll have students tell me that, well, I still have to get k by itself, so I have to divide by the negative 11 on both sides. And that is incorrect because k is already by itself. This negative 11 isn't here mathematically. It's only there for informational purposes. The best analogy that I've come up with to explain how to think about this is it's like a pop-up window, which we could minimize if we want to. So we could just minimize this pop-up window and just write k is equal to negative 44. Right? It's the negative 11 is only there for our information to let us know what was plugged in for x. It's not there mathematically to be manipulated like by dividing or by adding or subtracting or whatever else you might think to do. And as I mentioned earlier, this is not multiplication, right? That's the wrong way to think of it. Right? Let me just undo that. So this is not multiplication. So dividing doesn't do anything to it, right? Division only cancels out something if it's a multiplication. These are not being multiplied. And so this is it. This is the final answer. So what you want to type into the box here is negative 44, and you're done. Right. Let's look at part B just to make sure it's clear how to do this. So we'll start over again with the function k of x is equal to 4x. We want to find, in part B, k of 9. That tells me everywhere I see an x, I'm going to replace it with a 9. And so I'll do the same thing on the right-hand side. Replace this x with a 9. We get 4 times 9, which is 36. And that's the end of the problem, right? K of 9 is equal to 36. And part C is going to work exactly the same way, except you're going to have a really big number because 29 times 4 is going to be kind of big. All right, so that's how function notation works. Looks like we have one more example of this, so I'll just do maybe B and C here, because C is a little bit different because it's not just plugging in a number, we're plugging in a whole other variable. But let's go ahead and look at the case where we're just plugging in a number. So I want to find f of 2. That tells me I want to use this equation, f of x, which is equal to the absolute value of x minus 1. I almost put plus 1 for some reason. This tells me everywhere I see an x, I'm going to replace it with the number 2. So I get the absolute value of 2 minus 1, which we can simplify. The absolute value of 2 is 2. 2 minus 1 gives me 1. So that tells me f of 2 is equal to 1. For part C, we'll do the same thing. We'll start with the function, right? We have f of x equals the absolute value of x minus 1. But this time we want to find f of a plus 1. So again, I'm going to do the same thing we just did on the last example. Everywhere there's an x, I'm going to replace it with a plus 1. So I'm going to do the same thing on the right-hand side. Wherever I see an x, I'm going to replace it with a plus 1. And then you try to simplify. And maybe in some other problems with other types of functions, you'll be able to simplify things a little bit more. But with absolute value, there's not really much you can do when there's a variable inside the absolute value. So I can't do anything with this. I can't combine the ones together because the 1 is stuck inside the absolute value. A is stuck in here. So nothing here is going to simplify. So in fact, that's it. That's all you can do with that. Replace x with a plus 1 and leave it the way it is. All right. Let's take a look at the next example. So here we're going to practice doing some more graphing. We talked about graphing in the previous section in 2.1, and this is really just more practice with that. Now they have the table, imaged here twice, but it's the same table. It's just this is the directions where they're giving you what the table should look like, and this is the answer where you actually type in the details of that table. So there's not that you don't have to do this twice. We just have one table to fill in, and on Math Excel they want us to type the answers into these boxes here. they are choosing the different values for x. So remember what we talked about, the generic method for graphing. You get to pick the value of one of the variables, you plug that into the equation, and let the equation tell you the value of the other variable. This time, however, they're not letting us make the choice, they're making the choice for us. So they are choosing the values of x for us. We will take their choice for x, plug it into the equation, and then let the equation tell us what y should be equal to, which again they're denoting as f of x, right? So remember, f of x, that function notation, that is the y variable. All right, so let's go ahead and I'm going to do maybe 2 or 3 of these, and then I'll just give you the answers for the other 2, and maybe you could try to figure those out on your own. So I'll do a negative one, so I'll do -2. I'll do a negative number. I'll do 0, because sometimes 0 does funny things. And then I'll do +1, let's say, and then I'll leave the other 2 for you to do. All right, so let's look at -2. So we're choosing, I say we're choosing, but in air quotes, right? We are choosing -2 because MathXL chose that for us. We will plug it into the function. So we're going to plug in -2 for x. So it's going to look like this, right? Plugging in -2 here for x. We will get -7 plus the absolute value of -2. Because again, we're replacing the x with -2. Then we will simplify. We get -7. Now you got to be careful with this kind of equation, plugging negative numbers into it. A lot of students make a mistake with this. The plus sign gets copied down, and then we apply the absolute value first. The absolute value of -2 is +2. So the negative sign is just going to go away. And we will get -7 plus 2, which is -5. So f of -2 is equal to -5. That's the corresponding value for y. That's what we're going to type into the box. So when x is -2, the function gives us -5 as an answer. And that's what we're trying to fill in on the table. When you choose this value for x, what value are you going to get for y? Right, when I choose -2 for x, I get -5 for y. All right, let's do 0. So we have x equals 0. We'll plug that into the function. So we get f of 0 equals -7 plus the absolute value of 0. Now, I find a lot of students try to avoid having 0 inside the absolute value as if that's a bad thing and it's not going to work out the way it's supposed to or whatever. But absolute value doesn't care about 0. It works the same way it always does. The absolute value of 0 is going to be 0. Right, so we get -7 plus 0, which is going to be -7. So f of 0 is -7, so that's what we're going to type into the box here. Right. And then I said I was going to do x equals 1, so let's try to squeeze that down here. So when x is equal to 1, plug that into the function. We get f of 1 equals -7 plus the absolute value of 1, which is going to give me -7 plus +1, which is going to give me -6. Right? So f of 1 is equal to -6. That's what I would type into the box here. So if you will pause the video for the moment and try to do the other 2 on your own, try x equals -1 and x equals +2, following the same procedure that we've done for the other 3 numbers, and see if you can come up with the result for that. So go ahead and click pause, give that a try, and then resume the video and you can check to see if you got the right answer. All right, so what you should be getting here, when you plug in -1, you got to be careful with that absolute value. What you should get is -6. Now, if you ended up getting -8, then you didn't apply the absolute value properly. So if you got -8, go back and look at that absolute value. The absolute value of -1 should have become +1. And then when you add that to -7, you get -6. If you plug in 2, you should get -5 here. And so you'll see there's kind of a symmetry with these answers. So let's plot these points, right? So remember the generic method that we learned in section 2.1. You get these handful of solutions. You plot them as points on the Cartesian coordinate system. So just to remind you, let me see if I can write in this direction. Not very well, but all right, this is going to give me the point -2, -5. Right? That's the x coordinate and the y coordinate. So that goes together as an ordered pair. That ordered pair is something I can graph. So let's go ahead and graph that over here. We have x is -2. Y is -5. It's kind of hard to line up, but I think it's right there. All right, so there's -2, -5. Okay, so that's -2, -5. So it lines up with -2 on the x, -5 on the y. We'll do the same thing for the rest of these solutions. So we'll have -1, comma, -6. All right, so which will be just a little bit below that. So it's going to be right here. Right? So that's -1 on the x-axis, -6 on the y-axis. We'll have 0, comma, -7, which will be this point here. And if you just stop there, it would look like these 3 points are lining up in a straight line, and you might think the graph is just a line. But here's where something different happens, right? Because the absolute value behaves differently when you start plugging in positive numbers versus when you're plugging in negative numbers, right? So for positive numbers, we kind of cut back the other direction. So when x is equal to 1, we're going to get -6 for y. So it cuts back up this way. And when we plug in x equals +2, we get -5. Right? And so what we end up getting, I think we had an example like this in 2.1. Absolute value functions are v-shapes when you graph them. And so we're getting this v-shape right here. And so let me connect those. These do make a straight line, but then we also get a separate straight line going to the left this way. Oh, got a little crooked there, but you get the idea. And so we get this v-shape. All right, so that's what the graph should look like. Now in Math Excel, you'll have to select the shape ahead of time. So make sure when you see that it's an absolute value, you pick the v-shape graphing tool, and then you plot a couple of points. It might want the vertex first, which is the point at the very corner of the V-shape. You plot that one first, you plot another point, it'll fill in the rest of the details for you after that. If you have any trouble with the graphing tool on Math Excel, please message me and I'll get back to you and help you out with that. All right. So same kind of problem here. We want to graph this function. We have f of x equals x squared minus 4x minus 1. We'll graph using the generic method where we pick values of x, plug them into the equation to get the corresponding values for y. Once we get those solutions filled in, we'll plot them as points. Hopefully a pattern will emerge, and then we connect the points according to that pattern. Right? So again, I'm not going to do all 5 of these. I think I'll do 3. Maybe I'll just do 2 this time, because it's going to be, I think this one's not going to be quite as bad as the one we just did, especially since there's no negative numbers. I'll just do 2 of these and let you do the other 2. Or the other 3, excuse me, and then we'll plot those points. So I'll do 0 is actually kind of easy in this case. I'll leave that one for you. I'll do 1. I'll do 1, 2, and 3, right? And then you'll do 0 and 4. So we'll start with x equals 1. We're going to plug it into the function. So we'll have f of 1. Now plugging in 1 on the left-hand side doesn't really do anything mathematically, but I still think it's a good habit to just wherever there's an x, you put a 1 in its place, and then the way this answer gets labeled is f of 1. That's the answer we're getting. Right? And we'll have 1 squared minus 4 times 1 minus 1. So we just simplify the right-hand side. 1 squared is 1. 4 times 1 is going to be 4. So when I multiply those together, I'll get 4. And then the minus 1 just gets copied down. Excuse me. And then we'll have the ones, the way I'm looking at this is the ones here are just going to cancel out. Positive 1, negative 1, cancel each other out. So we just get -4. So f of 1 is equal to -4. So that's what I would type in here. Right? When x is equal to 1, y is equal to -4. Right, let's do the same thing with 2. So I'll plug in 2 for x. We'll get f of 2 equals 2 squared minus 4 times 2 minus 1. So it's a pretty conventional thing to do when you're plugging in a number for x. If there's multiplication or exponents happening to it, to use parentheses. I kind of left that off here, but when it's a positive number, you're kind of safe just leaving no parentheses when you're squaring it. But if it was a negative number, you definitely want parentheses there. So a good habit is just to use parentheses every time. So I made a mistake there. I should have used a parentheses. All right, and then we're going to simplify. We're going to simplify. So we'll get 2 squared, which is 4, minus 4 times 2, which is 8, minus 1. So we copy that down. Again, plug that into your calculator or crunch those numbers however you want to do it. You should get -5. All right, so f of 2 is equal to -5. All right, so we'll have -5 here in that box. And then let's do x equals 3. Let me pick a different color so it kind of stands apart. All right, so we'll plug in 3 for x, so we get f of 3 is equal to, let's use parentheses here, 3 squared minus 4 times 3 minus 1. Simplify, we'll get 3 squared, which is 9. 4 times 3 is 12. minus 1. And so we'll get negative 3 minus 1, which will be negative 4. So f of 3 is equal to negative 4. Sorry about that. That was pretty bad. Sorry, I moved the window, the recording window, so I apologize for that. Hopefully it wasn't too jarring when you're watching the video. So we get negative 4 here again. And you'll see there's kind of a symmetry going on, just like there was in the previous example. So go ahead and pause the video. Try to find the corresponding values for y when x is equal to 0 and when x is equal to 4. And then resume the video to see if you came up with the right answer. I'm going to put the answer here in just a second. All right, so what you should come up with here when you plug in 0, 0 is kind of an easy one, because if you plug in 0, those terms just go away, and all you're going to have left over is the negative 1. So this should be negative 1. And I just kind of know from the symmetry that we're experiencing here, and I kind of know how these graphs behave, that this is also going to end up being negative 1. So you should find that you got negative 1 for both of your answers. So let's plot these as points, right? So this is going to give me the point 0, comma, and I can't seem to draw arrows very well. Let's try that again. It's kind of bugging me. Okay, so let's try it again. Arrow. Okay, that's better. 0, comma, negative 1, right? So this solution here gives me this ordered pair of 0, comma, negative 1. 0, comma, negative 1 is a point that I can graph on the Cartesian coordinate system. So I'm going to graph it right here, 0, comma, negative 1. We'll have 1, comma, negative 4. That's going to be this point right here. We'll have 2, comma, negative 5, which will go just a little bit lower. All right. We'll have 3, comma, negative 4 again, which will be right here. And then we'll have 4, comma, negative 1, which will be just below the 4. And the shape we're getting, it's not a V shape this time, because if you try to connect these 3 points in a straight line, they don't quite connect in a straight line, right? It's more curved. So what we're actually getting here is a parabola, which is probably best described as a U-shape graph. Right? So let's go ahead and see if I can draw that. So it should be curved, and it goes it's not completely a vertical line like I've drawn here. That's a little bit too vertical, but it does go up pretty sharply. So maybe something more like this. Let me see if I can do it over here a little bit better. So yeah, maybe that was a little bit better. And it should be symmetric. I don't know. Let me try that one more time. I'm not too happy with it. Let's try it one more time. Okay. So let's try the right-hand side first. I still almost did the same thing. Okay. And then the left-hand side. Okay. It's kind of a mess, but you kind of get the general idea, hopefully, of what that graph is supposed to look like. Hopefully you can draw better than I can. All right. And so that's that graph. And this is a function as well. And you know it's a function because they're using the function notation, which means that, and we experienced it, right? When I pick a value for x, I only get one answer for y. That happened every single time, right? When I picked x equals 1, I plugged it in the equation, I only got one answer for y, which is negative 4. That's what functions do, right? And so that's and they're easier to deal with because of that. Because if I was getting more than one answer here, that gives me more than one point to graph. It becomes a mess at that point. So this is behaving like a function, and they're using the function notation to indicate that it's a function. All right. The last topic that we have in section 2.2 is the vertical line test, which we use to determine when a graph is the graph of a function. And so there's a couple ways you can word this. So let me see how I worded it this time. So if any vertical line would cross the graph more than once, then the graph is not a function. So given the graph, if you can draw vertical lines on that graph, now remember vertical goes up and down. If I can draw a vertical line on the graph anywhere that would cross it more than once, then it ruins the whole graph and the graph is not a function. So all I have to do is try to spot some place where I could draw a vertical line that would cross it more than once. And then I would know that graph is not a function. If you're unable to do that, if no matter where you would draw a vertical line, it would never cross the graph more than once, then the graph is a function. So this is called the vertical line test. So let's apply this test to a few different graphs. So for example, if we look at this graph here, if I were to draw a vertical line anywhere, and again, I'm going to do my best to make this as vertical as I can. It's kind of hard to do with the setup that I have. Oh, that's pretty good. So here's a vertical line. How many times is it crossing the graph? Only once. Now, the reason this works is because when you choose a vertical line, you are choosing an x value, right? So this vertical line, if you look here, it's crossing through 2 on the x-axis. This vertical line represents all the coordinates where x is equal to 2. So I'm choosing a value for x. I'm choosing x equals 2. And however many times it crosses the graph is how many different answers you're getting for y. It only crosses the graph once at this point here, so there's only one possible answer for y when I choose this value for x. When x is equal to 2, there's only one point on the graph with x equal to 2, and it has a corresponding value of y of -1. I don't know, that sounded kind of weird when I said that. So x equals 2 has only one corresponding value of y, and it's the number -1. And we can see that on the graph here, right? We have this point at 2, -1, and it's the only point on the graph with x equals 2. So there's only one possible answer for y, which is -1. And that's going to be true no matter where I draw a vertical line. It will only ever cross the graph once. So here, no matter where I try to put a vertical line, it only crosses the graph one time. That means no matter what value of x I choose, there's only one possible corresponding value for y. So it's a function. There's no vertical line here that will cross the graph more than once. That makes it a function. Contrast that to this graph, which appears to be an oval, right? If I draw a vertical line here, let's say, so I'm choosing the value x equals -1, right? That's this vertical line that's passing through -1 on the x-axis. So I'm choosing -1 for x. How many times is this vertical line crossing the graph? It's crossing it twice. So there's 2 points on this graph with an x-coordinate of -1, meaning there's 2 different y-coordinates that correspond to this particular x-coordinate. So it's not a function, right? I'm choosing a value for x. I'm getting more than one possible value for y. It's not a function. So however many times it crosses the graph is the number of corresponding values of y that you're getting. 2 corresponding values of y means it can't be a function. So this is not a function. All right, so hopefully that makes sense how that ties back into the definition. But if you want to keep it as simple as possible, it really is just a matter of if you can draw a vertical line that crosses the graph more than once, it's not a function. Otherwise, it is a function. So let's take a look at this graph here. So this is kind of a crazy looking graph. It's these little sharp, jagged, I don't know how you want to say this, like a mountain range or whatever. Is this a function? So it's definitely an unusual looking graph. It looks pretty complicated. It looks like it'd be hard to deal with. But that's not how we decide if something's a function. It's a function if it passes the vertical line test. Does this graph pass the vertical line test? So pause the video for a moment. Decide what you think. Do you think this graph is a function? And then I'll let you know here in just a second to see if you had the right idea about it. All right, so this graph is indeed a function. So if you draw a vertical line, oh gosh, that's not a very good vertical line. Let's try that again. So let's try, I'll just try to follow the line on the graph here. So here's a vertical line. How many times does it cross the graph? Only once. And no matter where I try to draw a vertical line, oh gosh, that wasn't very vertical either, but you get the idea here. No matter where I put these vertical lines, they only ever cross the graph one time, and so this will be a function. For each value of x, there's only one corresponding value for y. So it's a function. So that concludes section 2.2 on functions.